All right, hello, welcome to lecture 14, where we will continue on the slides from last time and then start some new ones about strings. But first, there is one question on the question sheet, so let us go to it. So this has to do with a problem in your homework, and it asks about a line that has a .sync method on cin, and the question is, what in the world is that doing? And this is something that I had to go and check myself. I did not write this homework, so I also learned about it. So apparently, if you call sync on cin, sometimes, and I think this was the point of the question, back in the day, or maybe on Cecil back in the day, the sync method on cin, if you called it like this, in some implementations of the C++ standard library, this line will just chop off everything inside of cin. So apparently, in some implementations of the standard library, where you type in like the word, I don't know, word, where C++ puts its cursor at the beginning, and then you called get, just get, yeah, you just called cin.get, which gets a single character. It'll put the cursor right here, usually, but apparently, sometimes, in some implementations of the C++ standard library, this function advances the cursor to the very end of the cin stream, which means it's then ready to get more things eventually when you type it. And in theory, this code on this website would have like completely blown through this whole word test, even though the E, the S, and the T hadn't been read after you called this get function. So sync sometimes, in some implementations, is going to get rid of the rest of cin's input, so then it can just start over again. So for this example, it's like enter a whole brand new word, and then it starts reading from that word, is the idea, even though it stopped after it read this first T on the first word. So that is the idea, but this is like a tricky thing, and apparently you're not supposed to use it because it doesn't always work like this. This is only possible output. And so I'm sorry for confusing anybody. I will definitely not test you on this function. All right. So yeah, apparently on my machine too, if you can get rid of this line, it doesn't really do anything. So, but sometimes it does something. All right. Let us now go to the rest of our slides from last time. We were here. And so we have a linked list, and we want to recursively find the minimum element. So again, let's pretend we have a linked list, and we want to recursively solve the problem of finding the minimum element in our linked list. So I'm going to put it in the middle of this example list just to demonstrate. So here's our list. There's the head pointer and everything. And the idea is our problem. Well, let's write the problem. Find the minimum data value inside of a linked list. All right, that's what we want to do. And we'll take the head, we'll just take a node star instead of a linked list star or anything. And we'll assume that this linked list has one node in it already, so that we can, so that head isn't null initially. So, or ever. What does this mean? All right, so this comes down to a base case and a recursive case, as usual. So see if you can think of the base case and the recursive case for this recursive problem. And remember that you're supposed to be finding this problem inside of itself. So in terms of a linked list, can you find a smaller linked list on which to solve the minimum, finding the min problem, and use that answer on that smaller list to build back up the minimum problem on the bigger list that you were originally given? So I think the easiest thing to start with is the base case here. So what's the smallest list for which we can find the minimum immediately? And the answer is actually not the empty list this time, because if you had the empty list, there's nothing there. There's no element in the empty list. So there's no minimum. So we have to have a size 1 list. Technically, you can alternatively have the minimum of an empty list return negative infinity, maximum positive infinity. But we're going to do it a bit more sane. So let's just assume that our base case is a size 1 list. Instead, our base case is a size 1 list. And what's the minimum of a list that looks like this? What's the minimum of all the elements in this list right here? Well, it's its only data value. The single data value is the minimum of all the nodes, because there is only one node. I hope that makes sense. That's the base case, single length, single size list, singleton list, we say sometimes. And then we have the recursive case. And I guess the trick is, at least for this class, anytime you have a recursive problem on a linked list, you're always going to break down this list into the first element and then the rest of the list. So the idea is you want to solve the problem on the smaller list and then try and use this extra node that you didn't consider to build back up the final solution. Okay? So let's think about that. So we'll make the recursive call on the smaller list. And we get to assume that that works, remember. So what's it going to give us back? That call gives us back, well, it's solving this problem. It's finding the minimum value. That call gives us back the minimum for the smaller list. So in this case, it's going to give us back, we can assume, if we call it with head equals starting at the 3 node, we're going to assume that our function gives us back, our recursive function correctly solves this problem on the smaller list and gives us back 1 here. And our job is to consider the minimum of the whole list that we started with. So we need to consider this node still. And we have 2 possibilities. So, I'll keep the 1 part here. We have 2 possibilities. We need to use the min of the smaller list to build up the min, or to solve for the min of the whole list. Oops. All right, so there are 2 cases. Where the min that we get back from this smaller list is the entire min of the list, and that is exactly what's true in this case. The min of the whole list is in fact 1, right? It's also possible for that to not be the case if I had something like this. Do you see the difference? So the way to find the minimum of the whole list is to compare the min of the smaller list with the data value that you haven't yet considered. And what do you need to do there? Well, get the minimum, right? Either the min is in the smaller list. I guess it's possible that the min could be equal to the data value of the smaller list, but let's not consider that, doesn't really matter. Either the min is in the smaller list, or it's the head's data value. In either case, you can return min, head's data, and recursive call the result there, and we'll get back the right answer. All right, so let's go ahead and code this up. I hope this makes sense. I encourage you to draw the stack diagram for this, by the way. But let's go to code, and now you see why this is asserting the fact that head is not null, because we need a size 1 list for our base case. All right, so let's see if we can quickly go to code. I'll actually try and copy most of all this from last time because that's helpful. And I'll save it in today's files. Let's call it min recursive.cpp. So let's see here. We did recursive sum last time. We don't need it anymore. Everything else is just boilerplate to get us stuff. And is this our favorite list? Yeah, sure. 40, 10, 50, 20, 40. And this is a case where the minimum is at the head of the list. All right, so let's recursive min, let's call it. And that's fine. So let's call it recursive min And what's going to return back is an int. Takes a node star for the head of the current list that we're considering. And we're going to assume that it's always a size 1 list. And I can assert that if I wanted to. And this is a built-in assertion function that requires a library called cassert. We'll look into that if you are interested. All right, and so base case, size 1 list, and then otherwise it's the recursive case. So if it's the size 1 list, how do we check for that? That means that heads next is the null pointer. That's how you check for a size 1 list. And immediately we know the answer. It's the one and only data value. Return heads data. Otherwise, we're in the recursive case, and we should find the min of the smaller list. So int min of smaller list is the result of calling our function on the smaller list, which is represented by head next, right? So if that's head, this is head next, and that's that references the smaller list, the head of that, because every list is represented by a pointer to its first node. So we're going to get that min of the smaller list, and we assume that this works as long as we build up that final solution correctly, right? So now build up the final answer by also considering the head, head data. So you can call the min function in CMath, or you can just do it yourself. I'll just be a bit more explicit. If head data is less than min of smaller list, well, in that case, we should return head data, because that one was smaller. That was the smallest thing. Otherwise, the min of the whole list was the min of the smaller list. All right, we'll return that. So in this case, actually we'll draw the stack diagram. Let's make this. And yes, indeed, the minimum is 10, but why does this function work? Well, now I have to draw something so I can scroll down more. There we go. So our function, we called it for main, and I'll be very quick and not complete and correct when I draw my stack diagram like last time. So we're going to call this function on 10, 50, 20, 40. So it's like min of 10, 50, 20, 40. And keep in mind what the code is. It's going to first, because it's not a size 1 list, it'll go and figure out the minimum of the smaller list so that it can compare the 10 to the minimum of that smaller list. So find the minimum of 50, 20, 40, please. And that's still not a single element list, so it's going to compare its 50 eventually to the result of finding the minimum on the smaller list, which is just the list containing 20, 40. All right, and again, it's going to compare its 20 at the head to the minimum of that smaller list that only contains 40 this time. And now we finally hit our base case, because the min of a single element list is that one element. So this is going to return back 40. That's the minimum of my list. All right, and this one's going to use that 40 to compare the minimum of the smaller list with its head node. And so that ends up being, the head node ends up winning. So 20 is what's given back. And then again, this is going to get 20. It's going to compare its 50 to it. Still 20. Now this is going to get 20 in the recursive call and compare its 10 to it, and 10 wins. So main gets 10 back to it. And that is our recursive call happening. And every time this returns, of course, these stack frames go away. All right, hopefully that makes sense. So that is recursive minimum finding. And recursion is quite useful. Sometimes it's easier to think about a problem, or in terms of recursion, sometimes it's even impossible to solve a problem without using a recursive kind of definition and solution. All right, so one last thing for these slides, something called helper functions. So we have this linked list struct that we made, and it would be nice if we could use it inside of our min function or our sum function. And, well, what if we called our function with a linked list instead? That's no longer helpful. That's no longer a recursive kind of function because linked list can't be broken down into a smaller list. Because remember, a linked list looks like this. It's something like points to the head, points to the tail. You can't really make a linked list object that holds the smaller list. It would take a lot of work. I mean, you can make another one that is like, oh, there's the head now, there's the tail now, something like that. But it just isn't as easy as nodes, where the thing you're pointing to, that's the first node. Consider that. Entire list, please. So the way to get around this issue is to write what's called a helper function. So you write two functions in total. You write a function that it can actually hold the recursive kind of parameter, and that'll be your helper function. And then the real function, the one that takes the type that you wanted it to take, that isn't maybe recursive, that one just calls the helper function. So I'm going to do this instead of for some linked list, because here's the example for that already. Let's do this for the min function that we just wrote. It's quite simple to just make a helper function. So instead of saying recursive min L head, let's say recursive min, or no, we want to use helper functions so that we can pass along L. L itself. Okay, so the idea there is, I wonder if I can, no, that doesn't help. The idea is we want another function. We want it to be called recursive min. Again, you can actually give it the same name in theory. But I won't insert, I'd rather not. So recursive min linked list, I don't know. Let's call it that. Why not? And it's going to take a linked list, star L, and what it's going to return is, well, it's going to actually do the, this function is not recursive. It'll call the recursive min helper function. Helper function is the one that actually does the work, but it didn't have the proper type in its parameter that we wanted. That was the only problem. So we're just going to return the result of calling our recursive function on the proper type that it wants, which is a node, L's head. Okay, so now, instead of couting that kind of result, let's pass along L instead, because that represents our whole linked list, and we like that. It packages everything up nicely. Now we can just pass along this, L itself, and everything works out just fine. Okay, so with that, that is the end of these slides. So let's now go to talk about some strings now. And so there are two kinds of strings in C++, which is a bit weird to think about. But we're going to go through both of them. So there are C strings and C++ strings. And right now let's talk about C strings. All right, and they're quite similar to arrays of characters, as we will discover. But they're a little bit different. So let's first talk about C strings. These are the kinds of strings that existed in the old language, invented in the 70s, but is still around today and very popular still. C strings. So the type of a C string is, well, it's either, because you have two options, because they are kind of like arrays. It's either char, bracket, bracket, where you have like a name of it over here. So char array or char star, because that's the same thing, right? The main difference between a C string and an array of characters is that a C string has a special extra character at the end of it. And that's called the Null Terminator character. It looks like this. It's a \0. That's the character. This \0 character is called the Null Terminator character. Okay, so we can write a string in C++, or in C, a C version of a string, a C string, like this: char s bracket bracket equals, and then I'll give some characters like hi. That is very necessary, that Null Terminator character, because that's how you know. It's kind of like a linked list in a sense. That's how C++, when it's printing stuff out, it knows when it's at the end of the string. Okay? Because strings do not need to have their lengths associated with them. At least C strings, they don't. So that's the one difference. So this is a C string because it has, because it's an array of characters, and it's terminated with a \0 Null Terminator character. This is a lot of work to write this, and we've never written stuff like this before when we've needed strings, so there's got to be some other way to do this that's prettier. People write a lot of strings, so the implementers of the languages, C and C++, they made a shortcut for all of this. There is shorthand for this. This line above is equivalent to the following: char s bracket bracket equals, hi, with quotes around either side and a semicolon. Hidden inside, at the end of this syntax, is the null terminator character. So by using this kind of string notation, this null terminator character is included for you, which is interesting. All right, so that is enough talking. Let's give some examples. So I made this C strings file. Now let's talk about what you can do with it. So this notation, again, make an array of characters, set it equal to this kind of string notation. It's going to fill in the array for you. It's completely equivalent to, again, to this. So exactly equivalent to the following: char s bracket bracket equals character B, character L, character A, character H, and then null terminator character. Okay. And so here is a string that is not a C string because it does not have that null terminator character, and we've used the array notation, so we've explicitly given all of the elements of this array. Okay, alternatively, you could do stuff like this. You can set it equal to this array right here, and then give it some extra breathing room as well. This is a C string. It ends with this null terminator character. It just has extra things that you could possibly put in it. This string has length 4. We don't count the null terminator character in the length, but can hold up to 99 characters, because you always need to use that last one as the null terminator. Okay? And C++ is nice, and it knows how to output C strings if you just give it to cout. And we've been doing that, actually, because oh man is argv an array of C strings. Char star is just the same as char array in this case. All right, so every time we call with command line arguments, we're giving to argv an array of C strings, which are all null terminated with that character, and we can give those to cout as we know. All right, so the first thing that I want to do is just go through most of these. Watch them work. All right, so the first thing I want to do is compile this, of course, and hopefully I haven't done anything wrong yet. So we've made these 3 strings. Let's print out the first one. That totally works. So C string's got a null terminator character implicitly. We've printed it out. All right, let's print out T2. There we should see just A, B, C, and D, because the thing after it, even though there's extra space in this array, we stop the string every time we see that null terminator character. All right, so we print A, B, C, D. And then this one is fun. If you print T1, this is undefined behavior, because this is not a C string. And any library function that expects a C string is going to treat the array that you gave it as one, and so it'll try to read past the end of this array, and you know that that never goes well. And it's going to keep going until it finds that null terminator character. And eventually it finds it, and this is fun because you can see how the memory is arranged inside your program. Apparently, after this T1 array came the string S. That was just the luck of my machine and my compiler. Isn't that cool? So that was undefined behavior, though. Anything can happen. Doesn't have to be like that. And then there's some cool library functions, because what's the point of C strings if you can't actually do cool stuff with them? And plenty of stuff has already been written for them. So you can do all these fun things in the C string library. You can search for things inside of strings. You can bring 2 strings together. You can copy one string to another. This is all very low-level stuff from the C language because it was written to be a very low-level language. But the first one, the one that's probably the most useful, is strlen. So that'll calculate the length of the string. Back in the 70s, they really liked to shorten everything, every title of their functions. All right, so strlen is going to just return the length of the string that you pass along. And so blah has length 4 because strlen does not count the null terminator character. Here's some other ones. Strcat stands for string concatenate. And concatenate just means put one thing at the end of the other thing. So this is essentially, you say strcat T2 and S. What this is going to do is it's going to say, make T2 whatever it was, and then add S to the end of it. So if this was like Python, you could do something like T2 equals T2 plus S, essentially. That's what it's doing. Or even Java. Okay, so that is what's going to happen there. So T2, because we gave it extra room, and that's the point we gave it extra room, because it can grow, it's going to change from ABCD to ABCD, and then at the end of it, we're going to put blah too. All right, so it's going to be ABCD blah. Beautiful. Which is apparently the same as T1 in the special case of undefined behavior on my machine. Beautiful. All right, so that's C strings. Fun stuff. Essentially arrays of characters, but with that one special difference. All right, now we have C++ strings as well, and we are used to those. So here is my Cpp Strings example, and C++ strings, they were written later in chronologically. C++ came after the C language, and so they're a bit more sane. So again, we can use this notation for C++ strings. And the type is string, and we have to include that library if we want to use the cool library functions. But you can do a lot of stuff with these C++ strings. Actually, one thing that I should say, C++ strings, or think of C++ strings as special structs, because really the string type is a special pre-made type. It contains the characters of the string, as well as possibly other information, depending on the implementation. And because this can depend on the implementation, it's not guaranteed or even necessary for C++ strings to have a null terminator character at the end of them. C++ might instead save the length of the string instead, so it doesn't need to know where the end is. It just knows how big that array is. But that's not really important right now. So here we're making a string called apple, and some of the cool functions that we can do to it is get the length of this string, and this is using dot notation. This is like a function that you call on fruit itself. It's like all the stuff that we were talking about in the fstream library. So you can say fruit.length, get the length of the fruit. Fruit.find. So find where the first L is in this string. Substring gets like a string starting at an index going for a certain length. You can erase stuff from a string. You can add stuff to a string. You can replace from a certain range of indices one string with another. And then we can do these cool things. So I've, of course, put this all here, and I'm going to show you them a bit slower now. So the first thing, of course, we can make any string that we want. And where do I want to stop? I want to stop here. Let's output its length. And anything that I'm talking about here, again, is not in the CString library, it's in the string library, okay? So these are functions on the string library itself. You can click string, and here are all the functions that exist as those dot, using the dot notation on a certain string, like size or length. And size and length are apparently the same for the C string library. All right, so back to the code. So we're saying fruit equals apple. It's a C++ string. And let's get the length, and oops, forgot to print that out. So the length of fruit, and again, you can give a C++ string just as easily to cout. It knows what to do and how it's special and how to print that out. And the length of it is 5, okay? And then here, we can get the position of a certain character. It gets the index of the first L character and output that. So the first L character in this string is at index not 0, not 1, not 2, but index 3, okay? So it should output it to us the fact that this string contains an L for the first time at index 3, okay? And you can find the second L by starting the find function in a different spot. I encourage you to read this documentation if you're interested in that. But here is where's the find function? Let me search for it. There it is. So you can use it with a second argument. Right now it's defaulting to the first index, the 0th index, but you can tell it to start searching at a certain position, a certain index of the string. Subster stands for substring, so make a smaller string. So what this is going to do is it's going to set this new string called part equal to fruit, what it has at index 1, so this is index 1, the P, and take 3 characters starting from there. All right, so it should take ppl. All right, that's how you read that, and that's what the documentation will tell you. So this call is going to start at the index 1 of fruit and take 3 characters from it and put that into this variable called part. And so we see ppl. And a lot of these work in that same manner by giving a starting index and then a number of characters to do something with. So this is saying fruit, erase from index 2 3 characters. So this is going to say, all right, go to index 2, this is 0, this is 1, this is 2. From there, delete 3 characters. So this will change apple to app, just AP. Oh, gotta save it. just AP, and we can add stuff to it now. Let's change it from apple to apricot. All right, so what this is going to do is it's going to say fruit, insert, starting at index 2, so go to index 2 and insert this following string. So remember it was just AP, so it's 1, 2, it's really AP, right, at this point. Index 0, index 1, index 2 doesn't exist yet, it's like there's nothing there. So start there, and that's really the end of the string. So start at the end of the string and add stuff. That's what it's doing. And so now we have apricot. Beautiful. And then we can bring it back, of course, by using this replace function. And so we have apricot right now. So starting at index 2 of this C++ string, replace the next 5 characters with the following string containing just PLE. All right, so index 0, index 1, starting at index 2, replace 5 characters total, 1, 2, 3, 4, 5. So all of this Recot part, replace that with PLE. Okay? So we should be back where we started. All right. And then we can do cool stuff with this next library. This is actually a C library. It has these two lower is alpha is alnum functions, and these will be very, very helpful for your upcoming lab. So let's go to this library, Cctype. What it does is it mostly has a bunch of functions that check things, and it also has some conversions as well. So it has all of these functions. So you give it a single character. All these functions take a single character and return a Boolean. So here are some functions that might be useful to you. Something like is a space character. This will return true if the character you give it is like the space character, the new line character, the tab character, things like that. You can check if a character is uppercase, check if it's a number, check if it's an alphabetic number, check if it's an alphabetic number or a numeric digit, things like that. All right, and then you can also convert character. So you can give this function a character and it returns back a character. That was the lowercase version if it was an alphabetic character. Otherwise, it keeps it the same. And then toUpper converts whatever character you give it to uppercase. Okay, things like that. Let's see here. Yeah, that's what I wanted to say about that. So let's now go back to the code. So this is saying, let's do just these first couple. This is saying, again, we have apple now. Fruit equals apple. This is saying the first character in fruit, change it to be the lowercase version of itself. So this will change apple to be, this will print lowercase apple, okay? And maybe I should show that. There it goes. And now we can do other things like check whether or not some of these characters were alphabetic. Check if they were alphanumeric. And this is all true because this first A character, if it's APPLE, at index 0 of fruit, it's an alphabetic digit, or it's an alphabetic character. And if it's alphabetic, it's surely now alphanumeric as well. So these should both return true. And finally, you can do that one thing that we wish we could have done over here in C strings. Instead of using strcat, well, if we had a plus operation. Well, we sure don't, but we do inside of C++ strings. That plus operator has been what's called overloaded, and so we can use it to actually add stuff. So, dun dun dun. I scrolled down because I think I gave away an answer to a future question on the slides. So this is now apple, apple, okay? With that, please now take a second to think about the answer here. So given all this code, this is involving C strings, what do you think is going to happen when all of it runs? And I will check my time. Where has it gone? There it is. 40 minutes. Okay. So what's happening is the following. So we made two strings, Mark and Jill. Now we're going to iterate through it. And remember, this is okay because there's secretly something in index 4, that's the null Terminator character. And it's going to take S2 and make it S1. So far, everything's fine. S2 became S1 in a sense, so it's going to be like S2 now holds the string Mark at this point, and then we run this stuff. And it's saying if S1 is equal to S2, make S1 art, and then print out these things. So this is definitely not Jill anymore. What's going on? Okay. I think I've pre-typed it. Yes. No, we want to go to C strings. Dun dun dun. All right, let me go and run this now. Ignore the comments for a second. All right. We have a few issues. So this is actually a compiler error, in fact, which you might not be expecting. So the thing is, you cannot reassign arrays in C++. These are basic types that you cannot reassign to. Okay, so that's the first problem. The second problem is, even if you could, this would never be true, because S1 is a place in memory, S2 is a place in memory. If you ask things like this, they're comparing pointers, remember that. And these are always two separate places in memory. They're two separate variables on the stack. So this will always be false, and you can actually do this. So this is in fact a compiler error. Dun dun dun. How do I want to talk about this? Yes. So it's in fact a compiler error because this right here does not work. You're not supposed to do that. There, I'll put 1/. Okay, so that's no fun. We don't like that. How could you have done it? Well, that's where these C string libraries come into play. You could copy one string into another by using strcpy, for example. Or you could go character by character and use this array syntax to change every character one at a time. But you can't do it in one fell swoop anymore because this is like reassigning a pointer value to this. So you can use that kind of syntax when you're initializing, but you can't use it when you're assigning. Okay? That's the idea. And even if you could, this would always be false because these are two separate places in memory. All right. We don't like that because remember that the type of S1 is char star, type of S2 is char star. And so this pointer would always be false, and you can't actually assign these things. So let's see if I can, instead of this, say something like it was true or something. And then we'll print out S1 and S2 as well. And even my compiler is very helpful here. It's like, no, it's always going to be false. So you're getting mark out of the deal if you could get rid of the compiler error. All right. So now, similarly, what happens when you run this code? And these are C++ strings now. Take a second to think about that. And the question all comes down to, this is supposed to be less than because the C++ strings don't have to have the null Terminator character. And the question comes down to, is that going to be ever true? Is this ever going to work? All right. And the answer is, oh man, are C++ strings nice to you? So let me uncomment this. And these are Cpp strings now. We end up with art mark. And let's talk about why. Let me remember to circle it though. So what's going on here? Why does all this work? Well, the first reason is this equals comparison is overloaded for C++ strings. That's really nice. Maybe I'll put it, no, I'll put it in the code. Equal equal is overloaded for C++ strings. It compares character by character for equivalence. So they don't have to be the same place in memory, because they never will be in this case. But if they have the same characters inside of the string, they're considered equivalent for C++ strings, which is beautiful. And also, assignment to a C++ string also works. So that's beautiful. So you can reassign S1 later. It's not an array anymore. It's a special kind of type that has this assignment operator implemented for it. All right? And so this is going to, first of all, make it to be mark mark. And then second of all, because it's mark mark, it'll change S1 to be art, and now it'll be art mark. Okay. That's beautiful, isn't it? And then finally, for the last thing in these slides, before I get into a couple extra fancier examples, let's talk about Lab 8. So you're going to be doing two things. Well, in addition to these two things, you'll be doing other things, of course, but here are two things that you will be doing inside of Lab 8. You'll be finding palindromes and anagrams using C++ strings. And so let's talk about what those are. So a palindrome is when all the characters, or is when a string reads the same forwards and backwards. So for example, and then also capitalization doesn't matter. So for example, race car is the same forwards and backwards because it's either R-A-C-E-C-A-R or R-A-C-E-C-A-R. Okay, that's the idea there. And so all of these are palindromes. So get rid of these capitals so that you can compare them properly. How can we do that, possibly? Well, think about using these functions, maybe. All right, that's a hint there. Then anagram is a bit different. You'll also be removing punctuation, spaces, and I think that's all. Punctuation and spaces, and also capitalization doesn't matter. An anagram is two strings. It's something that, it's a property that can hold of two strings at a time. So two strings are anagrams of each other when they contain the same characters. In the lab, capitalization and space/punctuation doesn't matter. And in real life, nobody cares about capitalization, but in the lab, in addition to capitalization not mattering, space and punctuation also does not matter. So these are anagrams, diba and adib, and then rats and mice with random spaces, and then in cat's dream with a little single quote. That is also an anagram still. So make sure to get rid of all of these capitals so that you can compare. Get rid of all these punctuations and spaces so that you can compare properly. And so yeah, all these are anagrams of each other. It's just when the words are jumbled. And then finally, when you're making these functions, why don't you need to pass the length of the string? Well, that's because C++ strings are so nice to you. You can call, where is it? Either size or length, and you immediately have that. So think of the C++ string as a struct that not only contains the characters of the string, but also the length of that string. All right, so that is all that I have for slides, and I want to give you some examples now. But also, In the lab, it specifically says that you can use only library functions that I have talked about in class to solve problems. So I'm going to teach you one library function that you could possibly use, hint hint, in solving one of those functions and implementing it properly. So here's a function called sort, and it is from dun 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 algorithm sort. There it is. What it does is it's a function, and you give it what you want to sort, the indices that you want to sort, and you have to use these fancy calls to these functions. So sort from the beginning of the string S3 to the end of the string S3. You call it like this. You can just memorize the syntax, or you can come to office hours and I'll tell you why this is necessary and what it's doing. Technically, this means you can sort like substrings inside of a string. But this is saying sort the whole string for us. And what this does is it's going to sort all the characters, because this is just like an array almost. So make Cpp Strings. It's going to sort all the characters to be in order. Okay? You might find that useful. Okay. So now, for real, let's give some examples, because we are now at the end of these slides. Let's see how much time I have left. Yeah, we're good. So I want to write two functions, one for C strings and the other for C++ strings. So I'll include IOStream, I'll include C string, I'll include C++ string, I'll have a main function. Okay. So I want to write two functions. The first is a count vowels function. Let me make a C string. And then I want to count the vowels inside of this string. And if you don't remember what a vowel is, let me define that for a second. This is going to take a string, returning an int. A vowel is any of A, E, I, O, or U. So we're not going to count Y. So the standard vowels, and so we're just going to count how many of these are in the string string S. So let me implement a function that does that, and how many vowels are in this? 1, 2, 3. Okay, so here's how we'll do it. So let's figure out how we can do this. So int count equals 0. Let's iterate through the string now. How do we know the size of this string? Well, we have two options. You could pass along the length of the string. That's fine. Or we can use strlen. Isn't that nice? Or we could find where the end of it is too. So let's do a few different ways. So let's do it this way first of all, and then we'll return count at the end. So now we just have to, for each character, check if it's a vowel. So if si is equal to a, or si is equal to e, or si is equal to I, or it's equal to O, or it's equal to U. That's all the bases. Count plus plus, and this accidentally tabbed over too far. There we go. That should do it. Let us run this now. And yes, there are 3 vowels. there's one issue with this function, and I wonder if you found it. Alternatively, what happens if I do this? Take your best guess. There are no vowels. What? Well, there are two ways to solve this. I could duplicate all these and check for capitals as well, or I could use my fancy library function in Cctype to convert every character to lowercase. And I think I'll do that. I'll change these to C, and I'll make C S of I, but lowercase. In order to do that, remember I need to include the Cctype library. Beautiful. And so now it's going to, doesn't matter if it started out being lowercase, it's going to make it lowercase if it's an alphabetic character, and then it'll count properly. Beautiful. All right. So alternatively to this, you could have used a while loop. You could have done something like, instead, done something like while S of I is unequal to the null Terminator character, and we'll have our int I equals 0. And then we'll do the same thing. Include all this. And that should, in theory, do it. No, I've got to do I++. There we go. So one way with using, oops, sorry, I already did count way up there. One way using strlen, one way without. So that's counting vowels. And now, let's remove the spaces from a C++ string. This will be useful as well. So let me make string S3 equals A space B space C space D space E. And let's cout remove spaces S3. So let's make a function called remove spaces that takes a C++ string and returns a new version of it without any spaces in it. Okay? Well, let's be fancy and efficient. Let's make this a reference, but we don't want to change that reference, so let's make it const as well. Oops. So now we're saving memory. All right, and so we're going to build up a new string. Let's start out being empty. And let's now iterate through every character in this string S3. All right, so for int I equals 0, I is less than S3.length, I++. Now we need to figure out, is the current character we're looking at a space character? How will we do that, you might ask? Ooh, we'll use this isSpace function. And it works not just for spaces, but for tabs and new lines as well. So if it's not space, we'll keep it. Which means put it inside of result. We'll add a single character to it like that. And then we'll return our final answer. Okay. Let's do that. And it just got rid of all of those spaces. And let's see here. One thing that we could do is use the C++ range-based for loop. I don't know if I want to talk about that. Let's do it for fun. So if you compile with C++11 standards, there's another way to do this for loop. Alternatively, if you compile with standard equals C++11, you can do this. Or later, you can do this. It's kind of like your standard for-in loop in other languages, like Python. So for every character, call it C, inside of S3. See if that character is a space. If so, keep it. Isn't that interesting? That is fun. So let me compile with that standard. So now I have to use G++, because make doesn't, by default, have that. I could make a makefile, though. G++ standard equals C++11 string examples.cpp-o string examples. Dun, dun, dun. Nope, forgot I. Sorry. This is again C. We're taking iterate through every character C in C3, or in S3. Sorry. There it goes, and again, it still works. All right, so let me go back to the normal version so that it'll work on all your machines if you just use make. And I think that's everything that I wrote down to talk about. So that was an introduction to these different kinds of strings. You have two options in C++, the old style C strings, and then also the new style fancy C++ strings. And with that, I'll see you next time.